After watching the first video I presented to you, you'd have seen some nice psychedelic colors formed by oil put on top of water. And the questions we're going to answer in these next few videos is to try to figure out why soap bubbles have rainbow colors mathematically. What kind of formulas do we need to use to be able to predict why they have colors? So one thing we would have done in the classroom is we would have blown bubbles outside and taken a look at it. And what we would notice is that when you take this loop and you dip it into the bubble solution, the bubble solution would be colorless. It would be clear. Okay, and when you blow the bubble, the bubble itself would also be clear to begin with, but over about 5 or 6 seconds, the bubble starts to get these rainbow patterns inside. In addition, if we would leave that soap solution in that loop and just kind of leave it hanging there for a while, we'd start to notice that these rainbow patterns would appear. So if you have bubble solution at home, or even just soap for dishwashing, you can even try to do this at home and just see that effect, just because it's an important thing to look at before we even talk about thin film interference. Now, most students would often think that these colors are made by something we know. Refraction makes those rainbow patterns when we talk about refraction through raindrops. And in the last videos, we talked about diffraction for higher level, and we saw that rainbow patterns can be made by diffraction. But that doesn't happen at all with these thin films. What is happening is that the thickness of the film causes the color. That there's a strong relationship between the thickness of the film and color formation. All right, and that's what we're going to try to piece together. Why does that happen? So what's really important is that you do not make the mistake and think that these colors are due to refraction or diffraction. All right, so another thing that you would have seen in nature, more if you don't play with bubbles, you'd see oil slicks or water on the street that lifts oil off the road. And when you take a look at it, you would see these rainbow colored patterns forming on oil floating on top of water. You could take vegetable oil, you can take fuel, any type of oil that forms a very thin film on top of water will make these colors. And so, like I said, the colors must have something to do with having a very, very thin film. In addition to oil and fuel, you can take plastic, okay, like saran wrap, the food wrap that you have, and if you really stretch it out to make that plastic very thin, you will also see these colors form even in the plastic. So these colors are not formed due to dye or anything else like that. It's due to an optical effect where light is being reflected off the surface of that film and causing some strange interference pattern, okay? And it looks like this. When light hits that surface of the oil floating on top of the water over there, it does two things. The light beam can reflect. Okay, I'm going to call that light beam number 1. Okay, so that is my reflected beam. Okay, and then the second part, instead of reflecting, that light can go into the medium, travel down a little bit, reflect off the surface of the water, and come back out again. And I would call this my refracted beam. Okay, so that beam number 2 went into the oil, it refracted, but then reflected and came back out again. Now it looks like these two beams are completely separate, but because this oil would be really, really thin, what would end up happening is these two beams would actually just overlap each other. They'd come out right on top of each other. And what we can see is that when two waves intersect, they create an interference pattern. All right, when two waves intersect, the law of superposition comes in, and we'd have to apply all the rules that we've been practicing for the past month. All right, so what we do see here is that wave number 2 does some magic down here. Wave number 2 has gone through a path length difference. Okay, so wave number 2 has gone down in the medium and it's gone up. So if this was my thickness, I'm going to call it T, the thickness, it would have done 2 times T thickness difference than the light that just reflected. So its path length difference is going to be 2 times the thickness of that oil. Okay, so if that oil has a thickness such that this wave is going to come out maybe a little bit shifted, or the wave comes out absolutely overlapping with the other wave, we can create an interference pattern. And that's what the next video is going to be about. Okay, so the important thing here is that you're getting an idea that when light is hitting a very thin layer of oil or a thin layer of any type of film, it reflects and then it refracts. And the colors that you're seeing from this pattern are due to interference when those two waves meet up. The extra path length that the second wave went through in that medium, in that film, is going to give it some math so that when it comes out, is that wave going to be in phase with the other wave on top, or is it going to be out of phase? If it's in phase, they're going to constructively interfere and we're going to see certain colors. So already I'm getting an idea that these colors are very specific to the thickness of that oil and probably due to something to do with the refractive index of that oil. And every thickness would have a very specific color. And we're going to learn about that in the next video.